What's up, gangsters? How about a little bit of CAD modeling in Fusion 360? Now, this video is going to be a tutorial about how to build a tractor tire. And for you guys that are, experienced in Fusion 360, you're not going to find a lot of new material here. This may be totally boring for you other than, just as a way to see what my rationale and my approach is. This is really more geared towards you guys who are learning Fusion 360. And as usual, that means it's going to be a little bit long because I tried not to just give you the steps. I try to tell you not just what buttons to push, but why. So that you can carry that rationale and that knowledge onto other things besides tractor tires. Because a lot of the stuff applies no matter what you're building in CAD. So anyway, without any further gum flapping on my part, let's get right to it. This is the goal. This is what the CAD model will look like at the end. So you can kind of see this is something that I'm building to as part of a model making project. These are going to be 3D printed, and they have some assembly features inside the wheel here that are not really part of what I want to explain. So just to eliminate sort of any confusion about that, what I really am going to talk about is how to construct the tire carcass itself. So let's start out with kind of going back to the basic starting point. This is the project, and you can see this monster has 8 of these large tires, and this is what I'm actually in the process of designing. So you can kind of get an idea of what the tires look like, what their sort of shape is, but it's also instructive to go over here and have a look on the old interwebs so that we can kind of look at some other tractor tires to sort of get a little bit more of a general idea. You can see that kind of the basic thing with a tractor tire is that it is a series of protrusions, or lugs, I guess is the technical term, sticking out of a donut-shaped carcass. And that's a bit different from your typical vehicle tire that is really like this one here. This is an ag tire, but it's made more like a vehicle tire. This is a good illustration. So you can see you've got a tractor tire, you've got this turf tire, and you've got this industrial tire. The industrial tire and the tractor tire, like I was saying, are really more a series of protrusions sticking out of a carcass. And that's really true of a turf tire or a regular vehicle tire as well, or something like this. But this ends up being more of a series of grooves cut into the carcass as opposed to protrusions sticking out of it. And you can model it the same way, but you also might do it. You also might take a slightly different approach. Anyway, the point of this is that what I'm going to be doing with the tractor tire is treating it as a series of protrusions rather than a series of cuts. So hopefully that all makes sense, and that's not too much preamble. There's another example of one that would definitely be just a series of cuts. That's a pretty easy one because you just make a donut, do some annular grooves, and you're done. But not so much with the tractor tire. So let's go back to the very beginning and take a look at how to build this. Okay, so first things first, and that's to create a donut that represents the basic shape. And this is where you're going to establish all of the basics like the diameter, the width, the sidewall height. This is also a good point to maybe talk about how tractor tires are sized. This tire, as you can see here, is a 460/85 R38. And all of those numbers mean something that can help you as a model maker to figure out what your dimensions are, because you may not have all of the exact dimensions. And as you're going to see, a lot of what I'm going to do here is going to be based on eyeballing it and getting the proportions correct rather than being real worried about getting the exact dimensions correct. However, there are some dimensions that really do need to be on the money. And diameter and width and sidewall height are really those three things. So let's take a look real quickly at what these numbers mean. Let's go back over here to this. All right, so you've got these numbers, 260. So in the case of the one I'm building, it's a 480 85 R38. So that first number is the tire width in millimeters. So, and I believe that that's at the widest point. So basically from sidewall to sidewall, not the traction surface. But don't get me betting money on that. It would indicate, sort of seem like from this illustration that that's what they're saying, but who knows. Then the aspect ratio, 65, what that means is that the sidewall height is 65% of the tire width. So that's an important thing to note. And then you've got the wheel diameter in inches. And the wheel diameter in inches is a good place to start because that's from bead wall to bead wall. So basically the part of the tire carcass that contacts this part of the rim right here. So that would, at least in theory, be this number right here. I didn't make this exact. I made it a little bit small so that I'd have some meat to work with, and I'll explain that when I get to the part where I create the wheel. But basically, this is where you'd start putting in those numbers. Your wheel diameter, your width from sidewall to sidewall, and you could put in a formula where this is going to be like I could say that this was this dimension, D15 times 0.85, because this is an 85 series tire. I did that initially, and I ended up not really liking the way it looks. And I think one of the reasons is because what I don't really know is that when they define that sidewall height, I don't really know where it ends. Like, I know it starts at the bead surface of the tire, but I don't know if it goes to the outside of the tread or to the beginning of the tread. It's kind of hard to say on a tractor tire because the tread starts so far down on the sidewall relative to where it ends up on the outside of the traction surface. So I ended up sort of fudging the sidewall height and just basically making it look good based on my reference photographs. So that's what I'm saying, is kind of getting into a little bit of that visual fudging. But anyway, this is the place where you're going to set up some of your most important parameters, and it's important to get this sketch fully constrained so that it's well behaved and you can modify it later, because as is the case here, I ended up doing quite a few iterations because when I got the whole thing done, I didn't really like the way it looked. I didn't feel like it really was proportional based on my reference photographs, and I ended up going back and tweaking it a lot. And so you really want a CAD model that's well behaved, and that always starts with good sketch discipline. And so that's what I'm trying to do here. This entire sketch profile is all black, which indicates that it's completely constrained, and I've got all of my dimensions set up where They're easy to get to and easy to understand. And I've tied this cross section of the donut to the origin so that it's symmetric on both sides of that, and that the origin is going to be at the center of rotation. That's just what makes most sense with a tire carcass. You'll notice this dimension has this f of x. That's what I was saying before, where you're using another dimension to drive this parameter. So basically all I did, because I want this radius to be the same as this radius, is instead of actually typing in 50 millimeters over here, I just put in D13. That way, no matter what I set this number to be, if I change it to 51, this one will automatically update as well. So that's kind of the power of using parameters and functions. Same thing here. I make this where it's always going to be 1/2 of that dimension, and it'll automatically update. It just, not only does it help you control your design, but it makes things just a little bit more efficient when it comes time to modify them later on. All right, so that gets us the basic cross-section of the carcass. And then the next thing is to just do a simple revolved feature. After that, it's just a matter of putting some big rounded edges or sides or whatever you want to call them to represent that curvature right there. And again, there's no way to know what that dimension is, so it's just making it look good. All right, now the next thing is I've got to start setting up some reference planes so that I can build the first tread lug. So let me turn on construction features here. Don't get too hung up on this stuff here. That's because this tire is a copy of the original. Okay, but plane 1 and plane 3 are what we're concerned with right now. So plane 3, plane 1. So I'm going to go ahead and show you the feature so that I can kind of explain it a little bit better. All right, so this is just the basic shape of the tread lug, and it's a loft. So what that means is a loft is this feature right here. And just like it says, it creates a transitional shape between two or more sketch profiles or planar faces. So what I had to establish was a planar face out here on the outside of the tread and a similar planar face on the inside. Now they don't have to be the exact same shape, but in this case, it makes sense to do that. So I made that decision early that they would be the same. But I also have to figure out how to position them, and that's what these reference planes are for. Because, as you can see, hopefully, if when I turn on the origin, you can see this plane. Let me see, here's a neat trick if you don't know this. You can grab a plane, and when the edge of it highlights green like that, you can drag it, see, like that, so that it's easier to see. That's a good trick to know. Now, hopefully you can see pretty quickly that, all right, that's the reference plane. And you can see that it is offset from the center line of the tire. And the reason is because if we go back over here and look at the reference, you can see that the treads extend across the center line. They do not meet in the middle, and they, like in this particular tire, they overlap each other by quite a bit. How much they overlap, that just depends on the particular manufacturer. But what I chose to do was make them overlap just a little bit. So this plane right here, plane 3, is offset from the center line by 0.4 millimeters. The other plane is out here, and it's going to be not quite tangent to the curvature of this surface. And you can see that because there's a little gap between this annular edge of this face and where the flat face of the tread lug intersects right there with the donut. Now the reason that I did that is because even though in theory the outside of this tread lug should be that planar face should be tangential to this face right here. Not only does it not absolutely have to be, but you will create mathematical problems by making these things intersect exactly. And I'll show later where that will come into play. But basically what I'm trying to avoid is this arc being coincidental with this arc, even though logically and mathematically it makes sense that they would be. All right, so hopefully that helps you understand how I positioned the reference planes. Now let's take a look at the sketches. Okay, so this first one, really straightforward. Okay, it's just this sort of truncated pyramidal shape. And what I've done is I've established the angle of each of the outside faces, the width there. You can see that this is still blue down here because I don't really care where that is. All I really care about is the outer diameter that's going to be represented by the outside edge of the lug. I want the inside edge to be inside of the donut so that I have a really solid intersection between this lug feature and the donut feature. All right, so now let's look at the sketch here. Okay, now this is where things get a little bit tricky. Not so much because of the difficulty of the sketch, it's not that at all. You can see what I've done is basically just produce the same sketch profile, same controlling dimensions and everything, but I've rotated the whole thing 6.5 degrees. Now, why did I do that? All right, so the reason is because that's the amount of offset that it takes over the distance from this edge to this edge to give this about a 23-degree angle. And you're like, okay, what? What did you just say? All right, so let me show you real quickly. This is pretty easy to see on this tractor. Okay, there's basically two types of farm tractor tire tread designs, two schools of thought. One is that these tread lugs should be oriented at about 23 degrees to the horizontal. And the other, I think there's another tire on here, is that it should be at 45 degrees. And you can see that with this different brand of tire back here on the back. They're sort of compromising by making it curved, but those are the two basic things that you're going to see with tractor tires. And you can see it pretty clearly here where like this one has the 45 degree angle, this one has the 45 degree angle. You can see the differences here. This one's got the 23 degree angle. It really comes down to the kind of soil that you operate in, whether you operate on hillsides, that type of thing. These tractor tire manufacturers have done all kinds of studies and experiments, and that's what it's basically boiled down to, is either 23 or 45, and I chose the 23 degree. So that's just kind of geometry. The amount of twist per se may be different according to the diameter of the tire and the distance from here to here, and you just have to kind of work that out. But that's where that 6.5 degrees comes from. Hopefully that makes sense. All right, so I'm going to shut these off. All right, the loft, okay, is again just going from this profile to this profile. Really straightforward, just connecting the two. There's no reason to include any guide rails or anything like that. It's the most basic kind of a loft. Why didn't I just do it as a straight protrusion? Well, because of that 6.5 degree twist. It's just doesn't work. Protrusions either go straight or they taper, but they don't offset. If you're going to do an offset, you have to do a loft. All right, so that gets me that thing. All right, now let's go on over here to some more defining features. Now, all right, it needs to have some rounded edges. Okay, so the first thing I did was round these edges, and that gives me a continuous tangential path to go all the way from this end point to the other end point. And this is where the reason for not having this arc be coincident with this arc comes into play. Because if I try to tell Fusion, or really any CAD package, that I want to start a radius right here, and there's also this arc for it to contend with mathematically, it's most likely going to fail. And this is just a thing when you're kind of strategizing how you're going to do radii, fillets, whatever you want to call them, is that you need to make the math as simple as possible because they're just computationally intensive and they can result in math errors, and that's when you get a fail. And this one in particular, because it's going to be a variable radius fillet, I need to have everything be as robust as possible. So that's what's going on here. This is a variable radius fillet. And basically what you do there is you are going to select an edge and you're going to define the end and the start, and you're going to put your values in. Okay, now right now it thinks that the whole thing is 1.5 millimeter. But if I add in a radius point somewhere in here, now I can define a different value, and you can see that it'll change. And this number right here represents the distance in percentage along that path where you've established this value. So it's basically 49.4% of the way from the beginning of the path to the end, and you can control that. I like to keep it simple. The main thing is that they all need to be the same on all of the, when I do the lug on the other side, I need to keep track of that value and make it be the same. Anyway, that's how we get this nice variable radius. All right, now the next thing to do is to make this into a radial pattern. And this is where we find out how good our geometry is. And a radial pattern is kind of computationally intensive itself, but the more complicated the features that make the radial pattern are, the more computationally intensive the pattern will be. And this has a pretty intense feature that it's trying to make a pattern of. But there's a couple of things we can do aside from just making sure that the base geometry is robust. One thing right here is you're going to have some options, and the more complicated the thing is that you're trying to pattern, the more likely you need to use optimized. And I don't know exactly what the math is that's going on in the little robot's brain inside of Fusion 360, but optimized will be appreciably faster with a lot of radial patterns. There are times when you can't use it, and if the pattern fails, sometimes the thing to do is to just, try different ones. Identical, I almost never use that. Identical would basically have all of these facing the same direction, and that obviously would not work. All right, now, annular spacing is almost always going to be full because you're going to go all the way around. There's 20 of these, which I got just from going and looking at the picture and counting the lugs and picking a number. Again, I'm not necessarily trying to make this exact, even though I'm labeling it as a Firestone tire. I just want it to look right. So that's where you get all of these values. With patterns, you can do faces, bodies, and features. I really always try to limit the number of bodies I'm working with. And so what I've gotten to at this point in the construction is a single body, and I'm going to pattern these lugs as features. All right, so that gets me wrapped all the way around, and things are looking pretty good. Now it's time to duplicate that on the other half of the tire. So I am basically going to create the same feature, just mirrored. Now, why didn't I mirror the original one? I could have probably, but mirrors are also computationally intensive, and so just to keep things simple, I chose to just basically duplicate the same sketch and give it the right amount of angular offset to place it halfway between two of the already constructed lugs, and that's where that 9 degrees of rotation comes in. And then of course on the other one it's going to be 9 minus the 6.5. So that's the basic arithmetic that gets that lug positioned in the right spot, and you can see it's got some overlap with the other one. Now I go ahead and add the, I did a chamfer to give the inside of it that particular look, and then added the fillet like I did on the other side, then the variable radius fillet, then we pattern, and this is, honestly, this is the hardest part of everything. This gets you the basic shape of the tire and the treads, and if you've gotten this far, you know, the rest really is kind of downhill and is just detail work. All right, so what we've got now is a thing that looks a little bit more like a paddle wheel on a steamer than it does a tractor tire. And so what we need to do is the final step in shaping the traction surface, and that's going to be a revolved cut to trim that down. Okay, that's what's going to give me that final cross-sectional profile, and that's why I left myself with plenty of meat on each of those tread lugs before, because I knew that I was going to come down and come in and shave those down. And again, this is just eyeballing based on looking at the reference photos to kind of see how rounded I wanted those to be at the top. You know, again, it's just pick a number because you're not ever going to know what that actual dimension is for this radius right here. So I think that looks nice. Again, it's symmetrical on both sides of the center line of the carcass, and that's a pretty simple revolved cut. I don't care if this top edge is constrained. We don't care where that goes. It's just this one that I want to know is correct. All right, so we'll back out of that. So that revolved cut then, super straightforward. We're just taking that profile and spinning it around this center line axis, and we're good to go. One more thing though that I need to do, I felt like I needed to taper the sides a little bit. Like I didn't want them to be just perfectly horizontal at where the tread block is. So I'm doing another revolved cut that basically just shaves some material off of each side. And again, these are symmetrical on both sides. I picked this 8 degrees arbitrarily because again, just wanted to look right. And that gives me a little bit more of a refined shape. Okay, so that's, I mean, look, you could quit right there. If you didn't want this tire to have a particular brand, if you just wanted it to be generic and you wanted to put a rim or a wheel on it, you could do that now, because this is the basic shape of the tire. Okay, so what do we have going on here? Well, I do want to put sidewall lettering on this tire. And I'm not going to go through a complete description of this part of the process. It's a tutorial unto itself. But basically what I'm doing here is creating a sketch profile of the letters. And in this particular case, I just used the text feature. You can do text on a path. That's what you've got right here. And you define that path, and that's what gives you the curvature. And then you can, you select the path and start typing in your text. And this lets you select the size, the shape, whether it's bold, italic, whatever it is, whatever it's going to be. And you're off to the races. And that's going to create an extrudable profile for the next step. Now, that's the easy one because that lets you just use an embedded font. If you can come close enough to the manufacturer's font, you're in business. But obviously for this Firestone logo, not so much the case. So what I had to do there is go into, I had to go find a logo, and you really have to get a good vector file. And then I had to bring that vector file into Inkscape, and you could use Illustrator, CorelDRAW, whatever your favorite is. I used Inkscape because it's free. And I figured out how to take that vector file and curve it about the right amount to where it was going to fit. And again, this was just eyeballing it. And then what you do is you're gonna export it out of your Illustrator package as an SVG, and then you're going to insert an SVG here into the Fusion 360 sketch environment, and that'll get you the outline of the logo. And it's going to be, you can see a bunch of little bitty sketch segments, and this is why you want a vector file, because if you do this off of a JPEG, it's going to be horrific. Like the first time I did this, it was literally hundreds of sketch segments. This is the clean and simple version, believe it or not. So you really have to operate off of a good clean vector. This is actually the original. Let's see. This is my. Let's see what I got going on here. This was. Oh, that was just for that thing. The original. I thought it was two separate sketches, but it's not. The original logo was just the outside outline. I did this 0.2 millimeter offset just using this command right here to create the inside profile, so that when I extruded it, it would have this hollowed out section in the middle of each letter. And that adds to the computational intensiveness, but it's the most realistic. I felt like I had to do that. So obviously we don't want them sticking out there like that. That's no good. But we'll fix that here in a minute. Now here's the next thing. This is pretty irritating. You'd like to believe that you could take these features and mirror those across the center line and put them on the other side, because I do need logos and sidewall lettering on both sides of the tire, because I'm going to have an inner and an outer, and the outside face on this side is the inside face on the other side, and vice versa. Well, unfortunately, if you try to do that, it mirrors the text and it's backwards, and that just obviously won't work. So I had to recreate the whole business over here on the other side, and you'll see that here in a second when it regenerates. And there you go. It's a real hassle. It's an annoying thing that I don't understand why Fusion doesn't allow you to just mirror that and it know what you're trying to do. I mean, it's pretty smart in so many other ways. This seems kind of like an inexcusable fail, but it is what it is. So we've got the text on both sides. Now we need to trim those down, and that's going to be another revolved cut that's offset from the sidewall to shave those letters down to the correct amount of sticking outness. That is a technical term, by the way. So, and you can see that's just curved. You can see that I just took the sidewall and projected it and offset the amount, 0.15 millimeters, that I wanted those letters to stick out. So pretty straightforward. All right, so now that definitely is the entirety of the tire carcass. Everything else that's going on here is for the wheel. Oh, that's a mark that I don't know what that's there for, but it's in the real one, so I did that. Let's see, I did add a radius to the outside corner there, and then I did a radial pattern of those, of that feature to get that all the way around. This was kind of a weird deal. I ended up doing it as a single feature on this one. I don't know how I pulled that off. And I did it as a radial pattern on the other side. Anyway, sometimes, yeah, that's a little sloppy, but it's there, it works. I just decided not to look a gift horse in the mouth because I didn't, I don't know how. Let's see, when I did this one, I just did that edge there, and so I had only one lug, and I patterned that. When I did this one, I don't know how it got all 20 of those edges. I need to go back and review that because that's better. Anytime you don't have to do a radial pattern or any kind of pattern, that's great. But I'm not sure how I managed to pick up all 20 of those edges when I did this fillet. Like I said, I need to go back and investigate that because that is better. All right, now, so that is definitely all of the tire. Now the next thing is to start building the rim. And so that's what's going on here. And again, that's just a series of revolved features and some patterns to get me everything that I need inside there. And now what I have is a wheel. Then I've got this as the left inside one. That's why it's got that LI punched into it so that I can keep track of them all during assembly. But anyway, that's that. That is how you build a tire in Fusion 360. Well, it's the way I chose to build this tire in Fusion 360. The thing you have to remember with all of this stuff is that there's always multiple ways to skin a cat. I'm not claiming this is the best way to do it, but it's a pretty robust way to get it done. There's no reason to overcomplicate things, and I think this is a pretty good example of that.